Today we'll have a seminar given by Dr. Manuel Izquierdo. The title is Soft X-ray Science at the European X-FEL. Manuel Izquierdo is working actually now in the European X-FEL. He has been there for 13 years. He studied physics in Spain at the University of Cantabria, but soon he left Spain to work in several places in the Netherlands. Then he moved to Paris to work at the synchrotron, at the LUR synchrotron, the former synchrotron of Paris. Then when Soleil was built, he moved to Soleil. He he was there for some time, and he soon got the possibility to visit the European X-FEL and decided to stay there. And since then, he has been developing some a nice experimental station with using soft X-rays. And today he will talk about these techniques and this experimental station. So, Manuel, on you want.
Thank you. Good morning, everyone. So it's a great pleasure to be here to talk about my favorite topic, which is soft X-ray science at FELS, in particular European X-FEL. I put a clock, so if you hear a noise, is that I'm over my time. So in principle, the presentation is part of the master class that I give at the University Autonomous. So for the students joining the master, there are some extra slides because I will not be able to cover all the topics. So I start with a brief introduction. So X-ray free electron lasers were first proposed in 1982 by these three colleagues, Devernev, Kondrachenko, and Salding. And they were, however, first realized in the sub-nanometer range in 2009 at LCLS, and the first lasing was done at 0.15 nanometers. Why it took so long is the need of very high-level technological developments that made this possible. The principle of X-ray free electron lasers is quite simple and somehow relates to classical lasers. So basically, in a classical laser, you have an amplification medium, and you have two mirrors, and then you bounce your seed beam back and forth, and after a few hundred meters, then your laser radiation goes out. In the case of X-rays, there are no mirrors that have a sufficient reflectivity. Actually, reflectivity in normal emission is basically zero. So, and then the idea that these three colleagues had, so okay, let's use a system where the amplification is going to be an undulator system, and instead of, because we cannot bounce the beam back and forth, so what we are going to do is propagate electrons a few hundred meters. So what happens is that at the beginning, you are going to have your electron packets organized like this, and they will radiate synchrotron radiation. And what is going to happen as they propagate along these 100 meters of undulators is that the interaction of the electrons with the electromagnetic field that they produce will bunch the electrons in these slices. And these slices will emit photons in a coherent manner, and as a consequence, you will end up, first of all, with a coherent beam, and second of all, because these electrons will radiate coherently, the intensity will be proportional to the square of the number of electrons compared to synchrotron radiation. So, and as you see, the principle is quite simple. After the first lasing in 2009, European X-FEL laced in 2017, and with a new capability, which is the possibility of doing this at megahertz. This was possible thanks to the development of superconducting acceleration cavities, because with conventional copper Linacs, the repetition rate was limited to a few hundred hertz. So the LCLS started doing this at 120 hertz. So some figures about European X-FEL. So it's 3.2 kilometers long from the injector, which is at DESY, to the experimental hall, which is here. There is 1.2 meter of superconducting Linac, where all these accelerator cavities are inserted, and they are cooled to 2 Kelvin using 200 tons of liquid helium. Then the long ondulators are located in this area. So basically there are 400 meters of undulator sections divided in three sasses, and each undulator section has 5 meters. And then you have the beamlines, the Harrick race beamlines. They have a length around 1 kilometer, and the Sophic ray beamline has a length of 400 meters, which is also challenging to align. But I mean, we needed to have these distances because the intensity of the field beam is so high that we needed to go very grazing and have mirrors of 1 meter length in order to not to damage the materials and propagate the beam until the experiment. So as here you see the paper with the first lasing, it was achieved in May 2017 at 0.8 nanometers. And what you can see here is the typical spectrum at this wavelength. And you will see that the bandwidth is large, and you have a lot of spikes. This is intrinsic to the method of SAS production. There are, in the meantime, new possibilities using self-seeding that allows to reduce this bandwidth, but the intrinsic basic is like that. So the price to pay in order to have a megahertz repetition rate is and accelerate the electrons up to 17.5 GeVs is that we cannot have a CW lasing because the superconducting RF cavities will not be able to handle all the power. And then so what we do is we have bunches of or micro bunches of 600 microsecond duration, and then 99.4 milliseconds of empty space that is used to measure detectors. And in this way, the power, the average power over time is pretty much reduced. In one of these bursts, you have up to 2,700 pulses, and the minimum spacing in time is 220 nanoseconds. When we run at 4.5 megahertz, we can, of course, decrease the frequency, and sometimes we do that because for some experiments it's more convenient. So the experimental stations are organized like this. We have, for the moment, 3 SASs built. Two of them are Harrick rays, and the third one is Sophic rays. Today I'm going to cover the Sophic ray part that we go from 270 electron volts, which is a little bit below the carbon edge, up to 3 kilovolts. And we have there three experiments. So in total, we have 7 experiments for Harrick rays. One covers high energy density science. The other is studying material imaging and dynamics. Then we have one station for femtosecond X-ray experiments, mostly in liquids. Then there is one station for single particle and serial femtosecond crystallography. And then we have an AMO and spectroscopy coherent scattering. These 6 instruments are the baseline of all the first generation FELs. At European XFEL, we have now another one, SXP, that I'm responsible of, because we want to extend the capabilities and also use the megahertz repetition rate to the limit. So I'm going to start talking about SQS. This is an AMO experiment, and basically what they want to do is they want to study three main topics. On the one hand, they want to study nonlinear phenomena with using the very high intensity that the FEL is producing in the order of 10 to 18 watts per square centimeter. And then basically they are interested in multiphoton ionization and multiphoton processes. On the other hand, they want to also study to do time resolved experiments using the short pulses available that range in the order from 1 to 30 femtosecond, and the idea is to do molecular dynamics and element-specific Sophic rays. And the third part is using the spatial coherence of the FEL beam. They want to do coherent diffraction imaging on different materials, including biological systems. So this is a layout of the SQS instrument. So the FEL comes here, and then so there is first an alignment laser, then there is a gas intensity monitor, because the SASE pulses, they are not like in a synchrotron all the same. They vary from shot to shot. So basically you have to do diagnostics of all the pulses independently. Then there is a differential pumping system, because the gas monitor works up to 10 to the minus 4 millibar, and then after it you have a focusing system KB that needs to be in the 10 to the minus 8 millibar. So this is the pressure drop is realized by this differential pumping. Then you have a laser encoupling system, and in the case of SQS, you have two experimental stations, AQS for atomic-like quantum system and NQS for nano-sized quantum systems. One of these two stations can be taken out, and then they can put an SQS REMIS on a reaction microscope to study coincidence. It's important to know that they have a very tight focusing. They have reached something in the order 1.3 times 1.2 micron square. In order to do pump probe experiments, besides the FEL, there is a pump laser. Actually, we have two outputs, one at 800 nanometers and the other at 1030 nanometers. The one at 800 nanometers is compressed to 15 or 50 femtosecond, and it has up to a maximum pulse energy of 1 millijoule at 188 kilohertz. And then it can be converted with second harmonic generation and third harmonic generation, or an optical parametric amplifier, and you can get up to 15 microns wavelength if you want. Then there is another beamline at 1030 optical output, and they can reach, in this case, 2 millijoules at megahertz repetition rate by default. These pulses, they are longer, around 800 femtoseconds. We are compressing them with multi-pass Heriot cells that will allow us to get down to 40 femtoseconds, and then you can also do frequency doubling, tripling, and so on. So now I'm going to give you a few examples of what can be done at the three experimental stations. So in the SQS station, so one of the first experiments, and that was extremely successful because it's the first science that was published at European XFEL, was to study a photon recoil imaging of atoms and to produce and to investigate stimulated radiation. So basically the idea, so this is the energy diagram level of neon. So you excite with the FEL at a given energy, and then there is Noye radiative decay, which is very fast in the 2 femtosecond time scale. But then you can generate also intermediate states, and through two different processes. On one hand, you have spontaneous Raman production, and in the other, you have stimulated Raman. So the idea that the colleagues had is, okay, so if we take a collimated beam, if you take a collimated beam of neon atoms and you send it to an MCP DLD detector, and then you hit this beam with X-rays of a given energy. So what is going to happen depending on if we have Raman stimulated or not. So if you don't have a stimulated Raman, so basically what is going to happen is that the neon atoms will have, on the one hand, a momentum that is given for the incoming photon, but then they will radiate spontaneously in all possible directions, and then this will give this kind of image in your MCP detector. However, when there is a stimulated radiation, because it has the same momentum as the incoming FEL beam, so basically what you will see is a line here. And so this is the kind of the simulation, and this is the experiment. So this is when they only had spontaneous Raman, and this is when there was also a stimulated Raman, and this was depending on the incident photon energy of the FEL. Then they did a characterization of how the stimulated is produced as a function of the incoming FEL, and they compared this with the simulations. So this is the top green curve is the simulations, and you see that there is a very nice agreement. One of the core business of the AQS station is to study processes like double core Hall spectroscopy, and this is something that is available only at free electron lasers, because you need a very high incoming photon beam. So in principle, when you excite with a photon, an atom like neon, so basically what is going to happen is, if there is only one ionization, this is probably going to decay very fast within 2.4 femtoseconds, and this will give you to a classical Auger decay. However, if you have a very intense photon beam, what might happen is that you can excite two core holes, and then basically there is competition between the two core hole ionization and the classical Auger, and then you can study this as a function of the incoming FEL photon beam, and then do these resonant Auger maps that would allow us to understand what happens with these short-lived states that you create in the intermediate cases. At the NQN station, so one of the experiments that we have done is imaging of nanostructure in superfluid helium droplets. So basically, the idea was first to produce nano droplets, and then the second thing we wanted to do is put some either atoms or molecules inside and see how they diffract. So this was done in 2019. This is the people leading the experiment. So basically, and then we studied with 1 kV photons, and then we can see here different situations. When you only have neon nanodroplets, what you see is this kind of diffraction patterns. If you dope them either with xenon or with silver, you see that the effect of the atom changes your coherent diffraction image, and then if you put some molecules inside, then you see that there is a huge change in the diffraction. So in the ReMi, so basically what they want to study is like a Coulomb explosion of molecules, and this is a first result obtained by the group. Rebecca Ball is a member of the SQS group, and basically what they did is they took this iopyridine molecule, and they hit with a very intense FEL beam, and then by studying ion coincidences, they could follow the dynamics of the explosion. So if you study coincidence of the ion plus, nitrogen plus, and hydrogen plus, you see these kind of reconstructions, and if you go and study ion, nitrogen, and carbon, you see as a function of time that the structure develop like this. Something that is interesting is that you do this by doing reconstruction of the moment, of the 3D moment, and the coincidence is possible to study if one molecule per pulse is ionized. And how do you get these very nice images is because you can align the data after they have been measured. The last interesting development that has happened at SQS is the production of attosecond pulses. You know that in 2023, the Nobel Prize in Physics was given to Pierre Agostini, Ferenc Krausz, and Anne Lhuillier for the production of femtosecond pulses. And so we have been looking into how we can produce this, and you have here some preliminary data. The femtosecond pulses are in the order of 500 attoseconds, And so basically this opened new possibilities, because if you see what has been possible with different pulse durations, so with picoseconds, we were able to study movement of atoms, with femtosecond charge transfer, and with attoseconds. So basically they have measured the movement of electrons in atoms, but electron-photon interaction has not been possible. But now with this development, it should be possible from now on. By the way, our colleagues have also managed to produce attosecond pulses in the hard X-ray regime, which is even more challenging. Now I'm going to switch gears to SCS, spectroscopy and coherent scattering. So this is the experiment that I joined at the beginning of my stay at the European XFEL in 2011. So this the idea of this instrument is to study 4 different topics. On the one hand, to understand ultrafast magnetism in nanomaterials. So I'm basically understand electron and spin dynamics, spin orbit-driven topological system, and laser-driven phase transitions. So then they have also interest in studying nonlinear X-ray matter and world-dense matter. And why is this? Is because with soft X-rays, the interaction between the photons and matter is much stronger. And so they want to study non-equilibrium electron hole dynamics, nonlinear spectroscopies, and what happens to matter in extreme conditions. Fourth topic is to understand quantum materials and control of the material properties and phases, and eventually even drive phase transitions with terahertz pulses. And then there is a last topic that is ultrafast chemical science, like bond breaking, bond activation, charge reaction, and water science. To study this broad range of science cases, so they have 2 different stations. One is a RIGS setup, and so basically this is the result of a consortium, and they have this RIGS setup that allows to work in the range from 0.5 to 1.5 kilo electron volts, so half of the range of the SAS3 undulator system, with a resolving power of between 1,000 or 2,000, depending on the monochromator that we use at the beamline. The transmission is 10 to the -6, and the time resolution between 30 and 150, with the possibility of also of moving the angle in this high precision floor. What do you want to study in a RIGS experiment? So it's a photon in, photon out technique. And basically, so you have here an initial state and a final state. And the photon out, if you photons can lose energy by interacting with several degrees of freedom of the system. For instance, with phonons, with magnons, with DD excitations, or with charge transfer. So if there is here a very nice review about the static RIGS. So one of the first experiments that was done, and is part of the commissioning of the RIGS station, was done by the consortia that has built this HRIGS altogether. So, and then is the study of nickel oxide upon excitation with 266 nanometer, that is energy enough to go from the O2P band to unoccupied Hubbard band. So, and then what they did, so you can take an absorption scan at negative time delays, and then a positive time delays, and then what you see is that your absorption spectrum is going to be changed into different places. One is at the pre-edge, and the other is at the L3 line. And then you can, they have studied the evolution as a function of time of these two features. So the data analysis is ongoing. The second station that they have is to do coherent diffraction imaging, is a small angle X-ray scattering and time resolved absorption spectroscopy. So as you see, there is a common part up to here, which is the lasering coupling, and you can recognize maybe the same elements as in the case of SQS. So you have an alignment laser, differential pumping, gas monitor, the KB system, and then the lasering coupling. In the case of of this implementation, what there is here is we call it FFT chamber, which is this cube, and there you can put a sample environment. The chamber is connected to a megapixel detector, LDSSC, which is a detector especially developed for European XFEL. It's a megapixel detector. The pixels are in the order of 200 times 200 micron squares. It can run at 4.5 megahertz, and you can measure 8 frames per pulse. You can change the position from wide angle to a small angle by using this tube, and basically there are some parts that are movable, and depending on the configuration you can just decide which is what you need. Okay, so one of the experiments that has been done with this is using a small angle X-ray scattering, is the formation of skyrmions in this cobalt platinum multilayer. So basically, this is the stereosis curve of this compound, and basically what happens is that so you start from like a homogeneous phase, and so if you would have energy enough, you would be able to go into an excited state, and from there to produce skyrmions. The way they did this is basically they shoot the sample with 3 pulses, and they measure with the FEL how the system was evolved as a function of time. So the first pulse either switches back to the initial state, and this will give you this image. Then the second pulse will give you this intermediate state, and with the third pulse you do the nucleation. You can see how the scattering patterns in the DSSC detector change as a function of the 3 different states. And so here there is a reconstruction of snapshots that allows you to see how the nucleation of the skyrmions is realized as a function of time, and how at the end there is some kind of coalescence. So a very interesting implementation that we did to do time-resolved X-ray absorption spectroscopy in transmission is the implementation of a technique that we call beam splitting of axis zone plate. And we did this because, as I've told you, SASE pulses they are all different from each other, and so basically what we needed to have is a way to measure absorption in which the normalization is done at the same time you measure each shot. So in order to do this, so basically what we have here is this beam of axis zone plate. So this guy is a combination of a diffraction grating and also a focusing zone plate. What happens is that when the monochromatic FEL impinges on it, so basically what we'll do is it will separate into 3 diffraction orders, 0, +1 and -1, and it will focus a little bit before the sample, and then you illuminate the sample that is here in a membrane. Normally the substrate is silicon nitride, and then the outgoing beam will propagate 5.2 meters, and then it will impinge in the DSSC detector, producing this kind of images. So what you normally do is in these 3 membranes, so when you have a thin film, the middle one is empty, so this you will use as an I0. The 1 + 1 will be the sample without the laser, and the -1 the laser, the optical laser will be on. And this will from there you can reconstruct the different pump minus and pump, and then all is consistent because you have the information of the 3 signals in the same measurements. This has allowed to reduce the signal to noise ratio. It has improved by a factor of something like 250, and is reaching the shot noise limit. So this is calculation in red for the shot noise limit, and then you can see here what are the results of the data analysis for one sample that was metallic nickel. You can use this with thin films, but what I did was something different. Is use them with a material which is lanthanum cobalt oxide that I've studied in the past, also with femtoslicing, and is one of the reasons that brought me to European XFEL. So, and lanthanum cobalt oxide is a very interesting system for the physics because it has a spin transition. High spin, low spin that has not been understood, and it has also very many applications in energy production. The problem with this material is that it has a rhomboedric structure, and if you grow it in a thin film, this will be changed into orthorhombic, and as a consequence, all the magnetic properties of the system are changed. So there is only one way to address this system, and this is by studying single crystals. So, and in this case, well, the idea that I had was to use the sample preparation technique that the biologists use to prepare the bio objects. So basically, they cut with a microtome, and you can see here these microcrystals of LCO with a maximum thickness of 100 nanometers that we were used with this transmission to do time resolve absorption spectroscopy. The second thing that we wanted to do is, you know, if you look, if you have a perovskite ABC and then you look at the oxygen KH, you are going to distinguish three different areas. So the first part is the result of the hybridization of oxygen with the B material, which in this case is cobalt, the 3D material. The intermediate region is the hybridization of oxygen with the A element, in this case lanthanum, and the last region in this particular case is the 4sp band, and this is related to bond length and distances. So, and then the idea is that if you measure the oxygen KH, you are able to understand all what is going on in the system. You can understand the electronic properties, the spin properties, and also the structure. There is the proof of principle we did here using femtoslicing, and what we wanted to do is to do an experiment in a free electron laser because you have higher FEL, and then you can study more in detail the fluence dependent and other things. We want to also give a twist. So the first experiment were done at 800 nanometers where you excite LCO about the gap. So in this case, what we wanted to see is how the dynamic changes when you excite with 2.5 microns, that is well below the gap. And so these are the results. So the data is analysis is ongoing. But what we can see is a little bit what we have observed at 800 nanometers. So if you look, there are modifications in all the oxygen KH. So it means that we have changes in the electronic and the spins. You have changes also in the interaction with the lanthanum, and then you also have modifications of the structure, which indicates something that we have observed before, that the charge, the spin, and the lattice in these compounds they are entangled, and this entanglement happen in the femtosecond time scale, because you can see here the time traces that there is a fast response of the system upon photo excitation. You can even give a second twist to the technique of the TRX absorption spectroscopy, and so you can decide, okay, yeah, the measurement with the microtome were not fantastic, can I do better? Yeah, so what you can do is you can take a single crystal and prepare a lamella, which has to be, again, in the order of 100 nanometer thick, and we have done this in cuprous oxide, which is a material that is relevant for catalytic applications. One of them is hydrogen production, and what is known is that the a specific high index phase that has different reactivity. And the higher the phase, the higher the reactivity. So what we did in this case was we prepare 110, that is like one of the low index surfaces, because we wanted to just to demonstrate that it was possible. So you can see here the lamella preparation, you can see the absorption spectrum, and then what we did was a pump probe experiment, and there we saw two things. On the one hand, we see here a prominent excitation at the pre-edge, and this is related to the production of the exciton due to the excitation with the laser. And then you see here that there are changes in the L3 line, and because we have the megahertz repetition rate, you can follow how this excitation of the system goes. In this particular case, we went up to 17.5 microseconds. If we would have more pulses, you can do up to 250 microseconds. And you see that some of the excited states are long-lived in the compound. I am now going to switch to the last topic, which is SXP, the instrument I was in charge to develop. So basically, it's an open port, and in the preparation of the project, in order to get the funding, although it was internal, to convince our council, so we had to justify the science cases, and it has to be something that goes beyond what is available at SCS and SQS. So basically, there were three propositions. One of them is to do complete time-resolved photoelectron spectroscopy. And because we have SOFIC rays up to 3 kilo electron volts, which is more than SOF, actually. So this opened the possibility of making the dream of simultaneous measurement, the valence band, the core levels, and the photoelectron diffraction of a material. So the spokesperson for this project is Kai Rosnagel at Unikiel, and also part of DESI. And the permanent station is provided by Professor John Hansen, University of Mainz. Then there is the group of Jose Crespo, who want to study highly charged ions as a laboratory for astrophysics, atomic physics, and fundamental research. And they can also understand some things of quantum electrodynamics. And then Philip Werner, that wants to study chemical bond activation. So if you want to have more information about the science cases, there is this technical design report that summarizes them all with some detail. So the technique that we have started implementing is time-resolved photoelectron spectroscopy on solids. So basically, unlike what we have seen at SCS, so this is a photon-in, electron-out technique. It's also based on the photoelectric effect that gave Einstein the Nobel Prize in 1921. And so basically, what you can do is then you can analyze the photoelectrons as a function of the kinetic energy, of the angle, of the spin, and from there you can get a very detailed information about all the properties of your material with the same sampling depth. There are two basic types of spectrometers, so hemispherical or time of flight. And for time resolve, for the moment, we are using the second one. You can study all systems that you want. So you have seen some examples of atoms at SQS, but you can also study molecules on substrate. You can study solids, bio-objects. Something that is important is that the photoelectrons, they have this universal curve. So basically, if the kinetic energy of your electrons is in the order of 45 kilo electron volts, you will have you will sample the last layers of the surface. If you increase to 3 kb, then you are able to sample depth in the order of a few nanometers. So basically, SXP is an ideal tool because you can study both the surface and the bulk properties of your material. So what we want to study, as I said, so is to realize the ultimate dream of measuring all the properties of your system in one experiment. And you will have to look here that this experiment of the atomic structure was not obtained with time-resolved photoelectron diffraction, because we have not been able to do this yet in forward scattering. So this was done with electron diffraction. So why is the limitation? Why I mean, photoemission at synchrotrons has been a very successful technique. However, at free electron lasers, there is only, there was until last year only one place in the world, which was FLASH, where this could be realized. And why is that? So the reason is that photoemission is pretty much affected by something that is a spare charge effect. This is very easy to understand and has been measured experimentally. So if you take a given sample and you excite with something with 10 to the 2 photons per square micron, so then you are going to measure your valence band with high fidelity, and you can also measure your Fermi surface. If, on the other hand, you start increasing the intensity from this value, you multiply by 10, you see that some electrons go above the Fermi level, which is not good, and then as you increase, you end up in this situation where the valence band and the Fermi surface are very much distorted due to the fact that you produce so many electrons and there are so many electrostatic interactions between the slow and fast electrons that in the end your image is blurred. If you know your system like this one, you can apply some corrections and then you get you can do the measurements also with high flux. If your system is new, then you are lost and then you will never be able to trust. So what is the possibility? The possibility is to do these experiments at moderate flux in the order of 10 to the 6 photons per second, and to have as many pulses as possible. So ideally, you want to have a CW source, and if it's megahertz, even better, like in a synchrotron. And currently, there is only one alternative, and it's superconducting accelerator FELs, because there is the only places where you have a megahertz repetition rate. So these experiments were tried at SACLA, running at 60 hertz, and I mean, you can do an experiment, but it takes you like weeks until you get enough statistics. So currently there are 3 places in the world where this can be done. So FLASH, that they can reach 300 electron volts in first harmonic and around 1 kilovolt in third harmonic. Normally it's a little bit lower, 800 electron volts. European XFEL, that we are able to do this up to 3 kilovolts. And then this year in the second semester, LCLS2 starts, that is going to run at up to 1 megahertz, although this year they will start only at 33 kilohertz, and they are going to cover at the beginning this range from 300 to 1.5 kilovolt, and then in China there is the SHINE project that is supposed to start next year. So basically right now, if you want to do some experiments, like you want to study photoelectron diffraction in forward scattering, there is only SXP at European XFEL where these experiments are currently possible. So I'm going to give you some examples of what has been done at FLASH at lower photon energies. One very interesting example is the excitation of tungsten diselenide. So basically, so they excited with 1.6 electron volts. So and with this, they managed to do a resonant excitation of the exciton system in the compound, and then they prove with 110 electron volts. And then what happens is something very interesting. So basically, when the sample is before time 0, when your sample is in the ground state, basically you have a Lorentzian shape for the core level of tungsten for F. However, upon creation of the excitons, basically what you see is that there is a population of the conduction band, and screening effects start being very important. And in this, what happens is that there is a drastic change of the line shape of your core level that cannot be longer described as a Lorentzian or void, which is the convolution of a Lorentzian with a Gaussian, to take into account experimental resolution. Then you have to describe the system with a Doniak-Sanjic, and basically there is a renormalization that is related to a screening of electron hole pairs around the Fermi level, and also there are the diagrammatic terms in the GW that and self-correlation energy that play a role. So if you do this as a function of time, what they were able to see our colleagues is that this material, upon laser excitation, goes into this processes. So, so this is before excitation. So there is an intermediate region between 0 and 1 picosecond where you have a significant population of excitons, but also some quasi-particles. And the physics here is similar to a MOD system. And then after some time, which is in the order of 1 picosecond, so the excitons are completely relaxed, and then basically you end up with free quasi-particles. Something that you can also study with time-resolved photoemission is magnetic phase transitions. One of the most interesting systems, but because it has applications for magnetic recording, is iron-rhodium. So iron-rhodium, as a function of the temperature, it has an antiferro to ferromagnetic transition with a lattice expansion of the order of 1% in 3 directions. So if you do a static experiment, what you are going to see is that in the antiferromagnetic, the density of a state at close to the Fermi level is very low. However, when you have the thermal transition and you enter into the ferromagnetic phase, you have here a peak that will show up. So, and as a consequence, the difference spectrum between the ferromagnetic and the antiferromagnetic is quite clear, and you can see that the transition has taken place. So the idea of the colleagues was to study this, a PAM probe, to see the dynamics, because there is a lot of research in the literature, and it's not yet fully understood what is the time scale that defines this transition. So what they did is they did an experiment pumping at 1.55 electron volts, so 800 nanometers. Basically, they probed with 123. And so what you can see as a function of time is something like this. So this is before time 0, that you are in the antiferromagnetic state, and then after after 0, what you see is that you have a lot of hot carriers at the beginning, and then immediately you see that your system goes into the ferromagnetic phase. There is a lot of debate in the literature because not everybody is convinced that the results are fully conclusive, but at least it's a step forward to understand what's going on. Something that you can also do, and is very interesting, is study photocatalytic materials as a function of time. One of the test bed is the Anatas phase of titania, and so because it's well known that this material has photocatalytic properties for many things. In this case, what they studied was the oxidation of CO, and basically what they did is, again, 800 nanometers. In this case, they went into the Sophie ray regime, therharmonic of flash, and then so they put CO2 and O2 at 3 × 10⁻⁸ millibar in the system, and what happens as a function of time. So if you put CO and CO2 and you don't put any light, so nothing happens. So then you can stay there forever. However, if you put a photo excitation, even if it is static, what's going to happen is that as a function of time, you will have the formation of CO2 due to the oxidation that is photocatalytically activated. And then they did the time-resolved experiment, and so basically what they saw is that so at the beginning you have only CO. And then what happens as a function of time is that around 2 picoseconds, you have a rapid formation of CO2. This CO2 is dissolved, and then your system is again with these CO2 adsorbed atoms, and you are ready for a next reaction. And that this happens without the formation of intermediate. So although the statistics is not amazing, you can see here that there are no extra peaks that show up. The last experiment I'm going to show is the realization of photoelectron diffraction, which is the dream. And then basically this was, sorry, I went too quick. Okay, there you go. So basically, again, 800 nanometer pump, 113 electron volt probe, and then they use this system, bismuth selenide. And basically, what they did was photoelectron diffraction And you see here, on the one hand, you see the experiment, on the other hand, you see the theory as a function of time, and then you can also extract some time traces, and then you see either the Gaussian width or the self-error factor as a function of time, and then retracing back to the distances of the layers in the material. Basically, they monitor the changes of the distant D1 and D2, which are the two surface most layers of the system, and what they see is that there is some kind of anti-correlation movement, and this is due to the fact that this is mediated by some phonons. So if in order to go forward from flash and to go to the higher photon energy, so we have built the SXP instrument. So this is the layout. So it's, as you see, is pretty much the same as the other ones. So with one basic difference, so we are much smaller, and for the moment we don't have an XGM because we want to do this with solids, because the intensity that we are going to use is much lower, and then we don't have to use gas attenuators. With solid attenuators and solid detectors, you can see how the I0 changes. So the important things to know is that it's equipped with a momentum microscope provided by the group of Gershon Hanse, as I told you before. So basically, this guys allows you to do either microscopy in P mode or angular resolve photoelectron spectroscopy, and for this reason we call them momentum microscopes. So they have a large acceptance angle in the order of 40 degrees. In order to do pan-probe experiments, we have an MCP DLD detector. There is this K resolution. The energy resolution is in the order of 130 millieVs, and for the moment we have spin integrated only. So there is the possibility of coupling another tube and then a spin filter, and then do also spin resolve measurements. We have the same pump laser as the other instruments, so with 800 and 1030, and then there is this OPA that for the moment is running at 118 kilohertz, and now is going to be commissioned for 562, and eventually we will have also 1.1 megahertz that for photomission experiment is very interesting. So this is a summary of the commissioning. So we have here the stations altogether is like 4-point-something meter long, and the reason is that we have this long time of flight that is necessary to get enough energy resolution. So this is how the so this is how the commissioning went. You can see here, this is the spot size that we got at the beginning with the FEL in the order of 2 × 37 microns, which is the best we can get with the current focusing system that we have. Then we put the optical laser on, we establish a special overlap, and then we also established a time overlap. So here is when we were preparing this. And then we started doing characterization, static characterization. You can prepare your experiments by using a chassis sample and basically a lab source is mercury lamp. And with this, you can get these type of images. So the biggest squares are 100 microns, the smallest squares are 10 microns, and inside these 10 microns, you have up to 1 micron squares. This is what you measure with the mercury lamp. And then we switch the FEL on the chassis, and then what we saw is that we were able to resolve something in the order of 200 microns, which was a little bit puzzling because we thought that we had this type of spot size. Well, we proceed and we measure core levels of gold and silicon, because this is the two materials that made this contrast in this chassis pattern. And so what we have done this year to continue the characterization when trying to understand this problem is we characterize the focusing again, and what we have seen is that we can get a beam that is much closer to the nominal parameters that we were expecting in the order of 2 × 37. And you see here, this is the FEL measured by the momentum microscope, and you see here one of these chassis, and this time this is 100 microns. So we are now in the order of something like 10 microns in the horizontal, and we still need to do some corrections because momentum microscopes, they have some chromatic effects, and we need to remove them, and from there we will get the final focusing. Even with this 200 micron spot, we had 3 community proposals the second semester of 2023, and the last one of them was able to complete a full experiment. So basically what they wanted to study is this kind of system. So basically they have a mica substrate, they patterned some gold structure, and then they cover it with tungsten diselenide, and then we wanted to study this resonantly with 760 nanometers and at 4.5 megahertz of the BP laser, which is something that had never been done at European XFEL. You see here, this is a picture measured with the SEM. This is the picture that we measure in the momentum microscope with a mercury lamp, and you see here that there are some different contrast, and this is because the tantalum diselenide is not just single flakes. Sometimes you have many flakes. And then to establish time zero, there is the first experiment that you can do is to measure surface photovoltage, and this has a time scale in the picosecond, and from there, by fine tuning, you can determine what your real time zero for femtosecond experiments here. And then in the last remaining time, we measure the shift of the tungsten 4F, and I mean there seem to be some indications of charge transfer, but the data is still ongoing. Something that is very important is that the FEL transmission that we need is very low, so it's 0.003% at 4.5 microjoules. However, the high repetition rate of European XFEL is necessary to realize this type of experiments. And with this, I want to thank Michael, Tommaso, and Sergei for helping me with sending me some of the slides they have, the group of SXP group for the great work they are doing, and to you for your attention.
So anybody has any question?
How difficult is to get beam time?
Well, it depends. For instance, SES, because they have the rigs and the other station, so basically they do rigs like once a year, because basically they need to change the whole setup. And the pressure is up to 5. I would say something between 4 and 5, depending on the beamline. And yeah, what is important is your science case, because basically the panel they are very interested more in the science behind that, sometimes in the complexity of the experiment.
In the beam station, what kind of preparation facilities do you have there? Can you do in situ growth?
Yes. So if I go back, how I to go? So okay, this is the main chamber. So you have here the interaction point. You have the momentum microscope with an hexapod to align the sample, and what you see behind. So this is a lead chamber, and on top of it you have a preparation chamber where you can insert evaporators and things like that. In principle, the lead and the preparation chamber, they are decoupled by a gate valve, so you can outgas and do your prepared sample while you measure the other, because the beam time is very precious.
And how do you compare in terms of flux with the 4th generation synchrotron radiation facilities? Because I think it's in coherence, this is much more it's clear.
Yes.
But in flux,
I mean, if it depends on what you want to do. For instance, SQS for nonlinear processes, double core homogenization, what they see in a synchrotron is almost nothing. And then you go to the FEL, and then the double core Hall ionization just skyrockets, and it becomes dominant over the single core. In the case of photoemission, like in third generation synchrotrons, you have to attenuate the beam a lot, because we already see space chance effects in a third generation synchrotron. Actually, these results that I present you from Gerd, this was measured in a this was measured in a synchrotron at Petra. So I mean, for photoemission, everywhere we have plenty. So what is not enough is the repetition rate, because we would need full CW. I mean, there are some, I mean, LCLS2, they will have this from the beginning. At XFEL, we are thinking of doing this, but the problem is, if you want to go CW, you have to reduce the electron acceleration energies, and then the high photon energies for high X-rays will be compromised. And so what we are going to start doing is extend the micro bunches. Right now they are 600 microseconds. The idea is to do them maybe 3 times longer, and then you can have more pulses per pulse, more pulses for your experiment. There is, like always, a twist. So I showed you that the DSSC can only record 800 pulses. So for the DSSC experiments, you don't need more than 800 pulses. For photoemission, we would need infinite number of pulses.
I find really amazing what you can do combining standard surface analysis techniques with time resolution. I found your examples very impressive. One technical question. I saw that for photoemission, for photoelectron spectroscopy, you don't use the typical hemispherical analyzer, but a time of flight analyzer. I imagine more than 1 meter long.
It's 2 meters.
2 meters
the
long.
top is 2 meters.
I suppose the reason is the time resolution, or what is the reason for that?
That's a very interesting question. Thank you so much. In principle, the catch is that you have a wide acceptance angle. So, and if I go, maybe, no, I need to go back. So, okay, if I go, no, it has to be forward. So and this is the idea. That has been put for. So basically, you can collect all photoelectrons in a cone of 40 degrees, because basically what you do is you put a very high voltage at the first after the sample, and basically all the electrons will be absorbed. However, there is a limitation, and this is the detector, because we have an MCP DLD detector, which basically you can measure 1, 2, maximum 3 electrons per hit. If you have more than that, then you have nonlinearities in the detector that also fake your data. So if we would have a megapixel detector with 70 micron pixels, momentum microscopy will be ruling. I have the feeling that we are going to go back to hemispherical analyzers, also with MCP DLDs. And what happens is that you get much better statistics by not measuring a cone of 40 degrees, just by measuring a slice around the direction that you want to measure. And then there is a second problem for those who like photoelectron diffraction, and providing that you have to apply a very high voltage, so you cannot, your sample has to be flat with respect to the nose of the spectrometer. So if you wanna study systems, I mean, grazing 60 degrees or so, you cannot do this with this current concept. So either you work from the sample side by putting on a wedge or something like that, or you put a hemispherical analyzer with a 30 degrees angle. However, the drivers of the technique, they are very keen on using momentum microscopy. So, but I think in the end, ideally, you want to have both, and this is what I would like to have, depending on what you want to to do. And the statistics with hemispherical is much better. It's also much better. I mean, but this is less of a problem because Heisenberg dominates you there. So basically, if you want to have femtosecond resolution, you have to give away a little bit of energy resolution. But I mean, still, you can also play tricks. And sometimes you can do picosecond and femtosecond. And with the mono, depending on how many lines you illuminate in the monochromator, you can also change the duration of the pulses a little bit and be beyond the Heisenberg limit.
Any more questions? Thank you, speaker.
Thank you.